Okay, good day everyone. Welcome to lecture 8 of our video lecture series for Physics 1. Okay, today's discussion would be on work, energy, and power. Okay, so in today's discussion, we will just be dealing with the following topics: work, energy, and power, and some additional topics that will be presented later on. Okay, so let's start with the idea of work. Okay, so work is a physical quantity which is said to be done on an object whenever there is a force that is applied to it. The last video lecture that I have presented to you, which is on Newton's laws, basically summarizes the effects of forces when forces are applied on objects. So either forces accelerates an object as presented in Newton's second law, or an object, a set of forces or forces would acting on an object would cancel each other so that the object would be in equilibrium, either at rest or either the object would be moving at rest or moving with constant velocity. Also, there is Newton's third law, wherein we have summarized the effects of the action-reaction forces, pairs of forces, whenever forces are applied to each other. On Forces are applied on an object. Now, for today's discussion, we will be dealing with the influence of the force whenever the force is successful in moving an object across a certain distance. Now, this idea of a force applied to an object such that a force is successful in moving an object across a certain distance, this quantity is called in physics. This quantity is called work. So when we say work is done on an object, we just simply say that the force has been successful in moving an object across a given distance. Now, the idea of work here is, of course, is a scientific work, and we should not confuse the definition of work with our basic notion of work, that is a job. So work here does not refer to a job, but work here refers to the scientific work, which is the product of force and distance. So this quantity, force times distance, is the quantification of having a force that has been successful in moving an object across that given distance. Okay, so work done by a constant force is given by the product force times distance move in a direction of the force. Now, for just like what is illustrated here, when the force is applied on an object initially at a given position, and that force has been successful in moving the object to say a final position, and the distance between the initial and the final position is given by d, then the work done on the object by this force is simply the product of force and distance. Now, of course, force is given in terms of newtons or pounds or dynes. Distance is meters, feet, or centimeters, or inches. And the work done should be expressed in the unit joules, pounds, feet, or dyne centimeters. Now, the international system of units accepted for the unit for work is the joule, which is the product of newton times meters. Now, in terms of whether work is a vector or a scalar quantity, work is actually a scalar quantity. So a scalar quantity, just like what we have presented to you in the early video lectures of our physics series, a scalar quantity is a quantity that is completely described by magnitude only. It doesn't have any associated direction with it, just like mass, time, and length. Okay, so work is simply a scalar quantity which is quantified as the product of the force times the distance. Although later on, it will be presented later on that a complete description of work as related to energy, we have to specify the direction for both the force and the displacement, and that would be later on. Okay, so the SI unit of work is the joule. It is the amount of work done by 1 unit force, 1 Newton force, which causes a body to move 1 meter distance. Okay, so if you apply a 1 Newton force on an object and that object moves a distance of 1 meter, then we say that we have done work equal to 1 joule of work. Okay, so a force may be acted at several angles from the direction of motion of a body. If a force is acted at an angle theta from the direction of distance, only the horizontal part of the force does any work. So, for example, in cases that when you apply a force in a diagonal manner, such as, for example, you are pulling a cart, or for example pushing on a lawn mower, or simply for example pushing on a mouse. um, so let's take the example of the mouse. When you push a mouse, you are actually holding the mouse and you're applying a mouse horizontally, not directly horizontal, but actually you're applying the force on the mouse diagonally. So when you push the mouse diagonally, you're actually having two influences of that diagonal force. So one is you push on the mouse horizontally, and at the same time you are pushing the mouse downwards. Okay, so our illustration here also illustrates that a force is applied diagonally and has two effects, one on the horizontal and one on the vertical. So just like the application of the force on the mouse, the application of the force is in a diagonal manner. So therefore, it has two influences: one along the horizontal, which causes the mouse to move forward, and one along the vertical, in the downward direction for the mouse, which keeps the mouse on the surface of the mouse pad, for example, or on top of the table. But the point here is whenever you apply a force in a diagonal manner, so that this force also becomes successful in moving the object across a horizontal distance, so that the force applied diagonally and the distance has this angle theta, then the work done by this force is simply computed by only a portion of that force which is in the same direction as the distance. So therefore, we only compute for the component of this force along the direction of the distance, which is of the same direction as the distance. Since the distance, of course, in this illustration is horizontal, so what we do is we just simply compute for the component of F along the x or along the horizontal, and that is computed as F cosine theta times the given distance. The y component of this force has no influence in moving the object across the horizontal. So therefore, this f sub y has actually no effect in moving or has no influence in moving the object across the horizontal distance. So which means there is no work done along the vertical. The only work done is the work done along the horizontal, and is computed as F cosine theta times the distance. Okay. No work is done when the direction of the applied force and the direction in which the object moves are perpendicular, just as what was illustrated here. The distance here is along the horizontal, and the component of the force along the vertical is F sub y is perpendicular to the distance. So whenever the distance and the force are perpendicular to each other, there is no work. Simply because if you apply the angle in the formula, the angle between two perpendicular lines, for example, the distance and the f sub y, the angle in between them is 90 degrees. So that when you substitute 90 degrees here, cosine 90 degrees, you could check this in your own scientific calculators. Cosine 90 degrees gives you 0. So therefore, the whole quantity equals 0, simply because cosine 90 degrees is equal to 0. This implies that whenever force and displacement or distance are perpendicular to each other, there is no work done. Okay, so no work work is done when the direction of the applied force and the direction in which the object moves are perpendicular to each other, or when the force is applied on the object but the object does not move. Also, going back, if you, of course, that is one case wherein the work done is equal to zero when the applied force and the displacement are perpendicular to each other. The angle between them is 90 degrees. Cosine 90 degrees gives you zero. There is no work done. The second half of this statement is, of course, when you do not apply any amount of force. Of course, when you do not apply a force, the force is zero, then the work done is zero. Okay, such as, or there is another case when you apply a force but the force has not been successful in moving an object. Also, the work done is equal to zero, just like what is illustrated here. The person is pushing against the wall, but the wall does not move. So although the force is not zero, the distance is zero, therefore the work done is equal to zero. Now, for the second illustration, the force is not zero. The force is actually going upwards. So, we know that the force applied by the person on the barbell is going upwards, of course, to support the weight of the barbell. And that is supposed to be going upwards. The weight of the barbell is going downwards. So, in order to support the weight of the barbell going downwards, the person has to apply an upward force. Now, considering the upward force, in this illustration, the upward force is just enough to support the weight of the barbell, which is downwards, but this force is not actually successful in moving the barbell further upwards. So therefore, there is no distance. So therefore, although the person would be eventually get tired in holding the barbell in this position, it doesn't mean that he is tired. Is that the work that the force applied by the person has been successful in doing work on the barbell. So in this case, in both cases, the work done on each of the objects, the wall and the barbell, is equal to zero, simply because the force indicated in each example are not successful in moving the object further. Okay, so just what was presented earlier, work done is a scalar quantity. So just like any scalar quantity such as length, length could be it could be positive, it could be negative, it could be zero, depending on the context of the given problem, if we associate a certain direction. Now for work could also be positive, it could be also negative, or it could also be zero. It was presented earlier the situations where the work could be zero. The work could be zero if there is no force. That's number one situation. The second scenario is that when there is force, but this force has not been successful in moving the object, so that the distance is zero, so the work done is zero. That's the second scenario. The third scenario is that both the force and the distance are not zero, but the force and the distance are perpendicular to each other, so that the angle in between is 90 degrees. Cosine 90 degrees gives you zero, therefore the work done is zero. So that's the three scenarios wherein the work done is equal to zero. Now let's talk about the situation where work could be positive, or work could be negative. Okay, so the force, as illustrated here, this is the distance, this is the initial position of the object, this is the final position, so that the object moved from this position up to this position by the application of this force, which was applied diagonally. Okay, so of course, the only component of this force that is responsible in moving the object across the horizontal is the x component of that force, which is parallel to the distance. So F parallel is simply F cosine the angle in between. Now, the force has a component in the direction of the displacement. The work done here is indicated positively. So when do we assign a positive value for the work? As illustrated here, the work done is positive whenever the force and the displacement, or the distance, are of the same direction. So whenever force and distance are of the same direction, such as this parallel to S, or the distance, then the work done would be positive. Now, when would be the work be assigned to negative sign? It is when the opposite is true. Whenever the force and the distance are of opposite direction, then the work done is said to be negative. So, what are the situations where the application of the force is actually opposes the direction of the distance? So, just to illustrate, for example, you are riding on a car, and you want to speed it up, the speed of the car. So what you do is you put on your foot on the accelerator. So putting your foot on the accelerator accelerates the car, meaning the speed of the car increases. So what happens here is that the car engine actually applies an additional force in the same direction as the direction of the movement of the car. Try to imagine that this object here, as illustrated here, is your car, and the applied force is in the same direction as the distance covered by the car. So that in this scenario, the force and the displacement, or the distance, is of the same direction. Therefore, work done on the car by the car engine is positive. Now, when is the work done on the car could be negative? So in actual scenarios for the car, such as, for example, when the driver wants to have the car slow down, so what the driver could do is to step on the brakes, for example, or perhaps gradually removes his feet from the accelerator, so that the car would eventually slows down. In this case, the engine applies a force in the opposite direction as the movement of the car. So that when that happens, the application of the force opposes the actual direction of the car. The car still moves forward, but this time the engine applies an opposite force opposite to the direction of the actual movement, so that the car would eventually slows down or would eventually stops. So in this scenario, the force and the distance covered by the car are in opposite direction. So in this case, the work done would be assigned as negative, since the force and the displacement, or the distance, are in opposite direction. So again, to summarize, when the force and the distance are of the same direction, the work done is positive. When the force and the distance are in opposite direction, the work done is negative. And lastly, if the work done could be zero if the force is zero, or the distance is zero, or when the force and the distance applied are applied perpendicular to each other, or the angle in between is 90 degrees. Okay, so let's take on a sample problem. Okay, so what you saw in the PowerPoint presentation is the same problem that is presented here in this Word document. Okay, so Steve exerts a steady force of magnitude 210 newtons on a stalled car. A stalled car is a car who suddenly that suddenly stops due to engine failure. Okay, so as Steve pushes the car, he was able to push the car a distance of 18 meters. The car also has a flat tire, so to make the car move in a straight line direction, Steve must push the car at an angle of 30 degrees to the direction of motion. So the question is, how much work does Steve do? Okay, so I will not be I will just be presenting to you the solution for the first question, how much work does Steve do? I will not be presenting the solution for letter B. Since the idea here, letter B, is expressed in terms of unit vectors, which was not discussed to you. We will be limiting our discussion on vectors that is expressed by distance and by magnitudes and direction only, not in terms of the unit vectors. Anyway, I will not be presenting to you letter B. Okay, so for the solution, we are given in the problem 210 newtons as the force. The distance is 18 meters, and the angle in between the given force and distance is 30 degrees. So this is simply a direct substitution problem. So work is simply FD times cosine of the angle in between F and D. So substitution, 210 times 18 times cosine 30 gives you 3,273.57 joules of work done on the car. Okay, so let's have another set of examples. We have work done by several forces. Of course, in reality, we can have one single force that could be applied on a single on an object, so that we can move an object. But there could be several forces that could be acting on the same object, but the overall effect of those forces could be in one direction only. So that this means that it is worth noting that the work done on an object could come from several application of several forces. So let's take, for example, this given problem. Okay, so the same problem is presented here in this Word document. Okay, so a farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters along a level ground. The total weight of the sled and the load is 14,700 newtons. The tractor exerts a constant 5,000 Newton force at an angle of 36.9 degrees above the horizontal. There is a 3,500 Newton friction force opposing the sled's motion. So the question is, find the work done by each force acting on the sled and the total work done by all the forces. Okay, so let us first identify what are those forces as presented in the problem that is acting on our sled. Okay, so obviously, one of the force would be the weight of the sled, which is given in the problem as 14,700 newtons, which is directed downwards. Also, the sled is of course obviously on top of the ground, and the ground provides a support force for the weight of the object, which is obviously the normal force, which is directed upward to counteract the effect of the weight. And next would be the applied force by the tractor, which is given in the problem as 5,000 newtons, directed at an angle 36.9 degrees with the ground. And lastly, the sled is said to encounter a friction force between its surface and the surface of the ground, and this amounts to 3,500 newtons. Okay, so the question now here is, what are the values of the individual work done by these individual forces? Okay, so we have the normal force, we have the weight, we have the friction, and we have the force by the tractor. So each of these given work then is expressed as force times d times cosine of the given angle in between the two forces, the force and the distance. Okay, so no, first let's compute for the work done by the weight. Okay, so the weight is directed downwards, and the distance is obviously horizontal. So therefore, the angle in between the work done, the force, which is the weight, which is downward, and the distance horizontal is obviously 90 degrees. So when you substitute cosine 90 degrees in the given angle, obviously this is equal to 0, since cosine 90 is equal to 0. The same goes with the work done by the normal force. The normal force is directed upward, and the distance is horizontal. So therefore, the angle between them is 90 degrees. Cosine 90 degrees is equal to 0. So even though you do not substitute the values for the work done or compute for the values for the normal force, the obvious values for the weight, the work done by the weight, and the work done by the normal force is 0, because of the substitution of the 90-degree angle in your formula for cosine. Now, as for the work done by the frictional force and the force by the tractor, let's have first the work done by the force of the tractor. So that is force by the tractor times the distance, which is 20 meters. The force done by the tractor is 5,000 newtons. Cosine 36.9 degrees, that gives you 79,968.47 joules of work done. And this is positive. Indicate the value for the work done for the tractor is positive, since the application of the force is, generally speaking, is of the same direction as the distance. Now, cosine 36.9 indicates that we are simply computing for the component of the force by the tractor along the direction of the distance. So 5,000 times cosine 36.9 gives us the component of the force in the same direction as the distance. Now, for the work done by the friction, friction times d times cosine of the angle between friction and displacement, or the distance, that is 3,500 times 20. Between 3,500 and the distance is, of course, the direction, the angle in between is 180 degrees. So that means cosine 180 degrees. You could try this in your own calculators. Cosine 180 degrees gives you -1. So -1 times 3,500 times 20, that gives you -70,000 joules of work done. So therefore, we have computed now for the individual values for the work done by each of the forces acting on our sled. Now, as for the work done, the total work done by all the forces, the work done, of course, obviously along the vertical is 0, since the normal force, the effect of the normal force and the weight is not successful in moving the sled along the vertical. There is no motion of the sled along the vertical. There is the only motion along the horizontal. So therefore, the work done by the normal force and the weight is obviously 0. Since we already computed for the individual work done, and if we're going to get the sum, that would simply sum up to 0 also. So the work done along the vertical y is equal to 0. The total work done would simply come from the sum of the force of the work done along the horizontal, and these are would come from the contributing work done by the force by the tractor and the friction force. So work done by the force of the tractor and the work done by the friction. So this is 79968.47 minus 70,000. That gives us 9968.47 joules of work done. Okay.